Previously, we have seen the TS diagram for flow process in centrifugal compressor when diffusion process is ideal. Now, we will apply the steady flow energy equation across the impeller. The impeller inlet section is section 1 and impeller exit section is section 2. So, across the section 1 and 2, that is across the impeller, we will apply now the steady flow energy equation. So applying steady flow energy equation across impeller, that is equal to Q minus WSF is equal to change in enthalpy delta H plus change in kinetic energy delta KE plus change in potential energy delta PE. Now the same can be written as Q minus WSF, that is equal to delta H, that is change of enthalpy across the impeller. So that is equal to H2 minus H1 plus change in the kinetic energy across the impeller, that is velocity at point 2 square minus velocity at point 1 square by 2, that is half C2 square minus C1 square plus delta P, that is G, change in datum head Z2 minus Z1. Now in this case we will neglect change in the potential energy and therefore this last term G in bracket Z2 minus Z1 is 0. Now the compression process is ideally adiabatic and therefore the heat transfer is 0 and therefore this Q is 0 minus WSF. Now to the compressor work is supplied and therefore work is negative and therefore minus W, that is equal to H2 minus H1 plus C2 square by 2 minus C1 square by 2. We'll rearrange this equation. So work W is equal to H2 plus C2 square by 2 minus H1 plus C1 square by 2. Now this term H2 plus C2 square by 2 is stagnation enthalpy. So we will write down it as H, since it is a stagnation it will be 0, 2 minus this term H1 plus C1 square by 2 is stagnation enthalpy at state 0, 1 and therefore it is equal to H01. So work done W supplied to the compressor is equal to H02 minus H01. We know that enthalpy is nothing but Cp into temperature. So that can be also written as Cp multiplied by H02, temperature at state 02, that is T02, minus again at this H01 it is equal to Cp into temperature at point 01. At 01 temperature is T01, that is T01 and therefore work W supplied to the compressor is equal to Cp in bracket T02 minus T01. Now if we observe the state at which these temperatures are taken is 02 and 01, which are the actual states, and therefore this work supplied to the compressor is actual work. Now similar to this, if we consider the ideal or isentropic process, then ideal or isentropic states are 01 and 02 dash, and therefore isentropic work can be written as Cp in bracket. Now instead of this T02 and T01, that is actual states, we have to take the isentropic states which are 01 and 02 dash, and therefore it will be Cp instead of this T02 it will be T02 dash isentropic temperature at state 02 dash minus T01. So this is the isentropic work or theoretical work that is supplied to the compressor. Next is isentropic efficiency. Isentropic efficiency can be written as the ratio of isentropic work to the actual work. Now from it is clear that Isentropic work is Cp T02 dash minus T01 divided by actual work is Cp in bracket T02 minus T01, and therefore the isentropic efficiency is equal to T02 dash minus T01 upon T02 minus T01. Important formula. Now if we observe here, then we are writing H02 as H2 plus C2 square by 2. Therefore I will write now as H02 is equal to H2 plus C2 square by 2. We know that H02 is nothing but Cp into T02, that is equal to H2 is nothing but Cp into temperature at point 2, that is Cp into T2 plus C2 square by 2. On simplifying this, we get T02 is equal to, we'll divide left hand side and right hand side by Cp, so that is equal to T2 plus C2 square upon twice Cp. So from this formula it is clear that temperature at stagnation state 02, that is T02, is always greater than that of static temperature, that is T2, by magnitude C2 square by 2 Cp.